we are extending now. All of the assignments so far have been with just triangles, and we are now going to extend it to any angle. And we are also going to introduce a radian measure. You guys remember when I was having you guys find on your calculators how I made you guys put them all in the right mode? Those of you who have the one that's like are nice, just these cheaper but nicer than the crappier ones, but these TI-30s, DRG is right next to the second button, and that's the button that you guys use when you guys are switching between degree or radian, okay? Radian is another unit of measure. Radians are usually involved, you guys will see pi a lot of times with radian. So pi, tell me some things that you guys know about like some formulas. Give me the formula for circumference. I know a lot of stuff circumference memorized. What's the circumference of a circle? That's an area, but good. Yeah, you use pi. That's good. You guys remember? Circumference is, anybody remember? It's 2 pi r. Okay, pi is this number that is consistent and around when you're like using circles. And I want to tell you where a radian came from. So I have a quick activity, and I kind of wish I gave you more time on this activity, but I'm going to pause the video for a second while I get something. Get recording again. So this activity is going to have you guys kind of discover something.
Can I use this?
Yeah, if you want to make a better circle with a compass, I have some compasses. I have some compasses in the closet, but I'm like not super particular because there's going to be some human error anyway. But if you're bugged that your circle isn't perfect, you are more than welcome to steal a compass. That's totally fine. Some of my compasses are broken, so they don't really like stay put with pencil. The angle wouldn't stay put. Okay. Okay, so while you guys are getting your pieces of yarn, I need you guys to see something, and and again, these are all going to be different size circles, okay? And remind me where the radius of the circle is. What's a radius defined as? It is. It's actually from the middle, okay? So it's not across the whole diameter is the full distance from edge to edge. So just from the middle to the outside of the circle is considered your radius. So the activity is this. Measure your radius with your yarn and then cut that yarn to that exact size. Okay? Once you have it, I want you to measure how many times that yarn can go all the way around the edge of your circle. And you're going to number it, right? So let's say you start here and then you measure the yarn, make a mark on your circle. Does that make sense? Pick up your yarn, measure the next section, put a mark on your circle. And I want you guys to tell me how many radii did it take to get all the way around your circle? And it might be a decimal, because you might only be able to fit like 4.5 of them. You know what I mean? Something like that. And use an estimate. Okay, what portion of your radius you got around? Okay, so how many? I can't talk and write sometimes. How many radii did it take? And then just make a note on your paper, and I'm going to come around and look, and you're going to say something R, like, or how many radii? Like 3.5 radians.
Well, I have a really big string.
All right, keep your measuring. Keep you are still measuring, that's okay. I'm gonna start, if you wanna raise your hand, I wanna start coming around and seeing how many radians it took for you to get around the edge of your circle. Okay, so whoever has it, I can come up with one first. Okay. Actually, maybe I'll just have people start yelling theirs up. Okay. Actually, no, because I don't want to influence people. Some people get a little bit. You can't change your answer once you have it. And what I'll actually do is have some people yell what they got. Okay. I see some still measuring, so I'm going to pause for just 1 second. If you're done with your equipment, I got to press play again. So we added everybody's up, and our average was about 6.07. So we just figured out that we realized that 6.2 average is about what, how many radians times 6.2 it took to get around a circle. We technically just calculated, like I said, circumference. That is what a radian is. A radian measure that we're going to introduce right now is the measure of an angle, theta. And we use theta a lot, if you guys are okay, but we've been using x on any triangles or even letters. But in standard position, and we're going to teach you what standard position, because we're going to start drawing angles that are not just triangles, okay? We're so used to angles only being stuck in a triangle, and I think I mentioned to you guys last time, we're going to be able to find all the trig functions for like a 900-degree angle or a 720-degree angle and things like that. And that's hard to imagine because you can't really draw a triangle that way. Triangles are only 180. Well, now that we have a circle to keep going around and around and around, we can do any angle. We can even do negative angles. Can negative angles be in a triangle? No, but they can when we learn how to graph on a unit circle. Okay. So, measure of an angle in standard position. This is what a radian is. That it intercepts the arc that it's on, like from here to here or whatever. Okay, wherever it intercepts that arc. Intercepts the arc that's equal to the length of the radius. So radians deals with essentially where you intercept a circle's arc in comparison to its radius, okay? And so that's why we have radians. It's always easier to show people where radians come from when I do this conversion now. Another reason why 2 pi, when we learn to calculate it, a full 2 pi is all the way around a circle, okay? That's your radian measure. 2 pi is the same as a 360-degree rotation before we start over again with the exact same direction, that exact same angles. Well, when you guys want to do conversions between things, and I want to change like a degree to a radian and a radian to a degree, we always times by essentially a 1. So if I wanted to turn 5 feet into inches, what would I times by so that I can convert that into inches? You've done the conversions before. You might have, this is a good ACT prep. What could be the units? What would I do if I wanted to convert this? Because units act like numbers. They divide out as well. So what would I times by if I wanted to convert it to inches? Yes, and the reason for this is because 12 inches is the same as 1 foot. And so technically it's a conversion ratio, even though you guys are used to timing it by 12. You are indirectly using conversions because 5 feet and 1 foot cancels. And so units cancel just like numbers would. And so if I want to convert something to inches, I make sure my inches goes on top in my conversion ratio. So we realize, oh, okay, 5 feet is the same as 60 inches. Well, you guys are going to be doing these conversion ratios with radians and degrees. If I want to convert a degree to a radian, I make sure, and by the way, to use easy numbers, if I were to divide by 2 and divide by 2, pi is the same as 180 degrees. So instead of us using 360, 180 degrees is halfway around the circle, okay? So just for easier numbers, we divide that out. And so it's pi and 180 instead of 2 pi and 360. So, because like I said, if I had had 2 pi and 360, why have bigger numbers when those can divide out to 180, okay? So, anyway, I make sure my radians are on top and my degrees on the bottom so that they can cancel. Or if I want to convert from radians to degrees, I make sure my radians are on top and then my degrees are on top and I convert there so they cancel. Pi is not always involved with radians, but if there is a pi, it's for sure a radian, okay? Because you guys can put pi in your calculator, but it's 3.14. You guys can put 2 pi in your calculator and it's 6.2. So 6.2 is still a radian, even though pi is not essentially there. Okay, so let's go ahead and do a couple conversions. That's probably an easiest part of your assignment. If we make you do a conversion on the test, it would be on the calculator side, just so you guys can do the math. We do expect fractions to be simplified, and we do expect radians, like that in a radian, to be left in fractions, like pi over whatever. So don't give me decimal on the radians. We want you guys simplifying fractions. All right, let's convert this degree to a radian, and then a radian back to a degree, okay? So if I want to convert 30 degrees, what goes on top if I'm converting 30 degrees into a radian? Pi needs to go on top. Pi radians over 180 degrees. And so what happens when we do this conversion is the degrees cancel, and I just get to simplify. So you guys are expected to simplify this 30 pi over 180. Now all of these specials divide evenly into 180. So that's why we learned the specials is they are nice, even whole number divisions when you guys try to decide how many 30-degree angles are there in 180. How many 45-degree angles are there in 180? How many 60-degree angles? They all divide into 180. And so that's why we use these specials so much in trig. And that's why we taught you the special angles last time. Okay? So how many times will 30 go into 180? 6. So this is also known as negative pi 6. So special angles are also known as what? Pi. This was 30. Shouldn't I get pi 6? Okay. I want to also talk about this in regards to the circle. Let's break this down as far as these specials go. We can get 6 pi's. So 6 pi 6 would represent 180 degrees. 6 pi 6 simplifies to just pi. So I can go 30, 60, 90, 120, 150, 180. How many pieces of pi? We can actually use pi if we want. Can I get in there? 6 of them. And so one little 30 degree is 1 pi 6. So it literally has a visual representation. I like radians because they're very visual. They're a very visual representation of our circle that we're going to be dealing with, okay? Let's convert radians to degrees now, okay? So if I want to times 5 pi halves, which is a radian, even though we don't have the unit there, what goes on the top and what goes on the bottom if I want to convert this one? Radians needs to cancel, so what goes on the bottom? Your pi radians, because my radians have to cancel, right? And then what goes on top? My degrees, because I want it to end up being a degree, right? So when I go to times this out, I end up having a 5 pi times 180. This is still in radians, degrees, I guess, but I'm going to cancel that. If you don't mind, I'll just cancel it so it doesn't get complicated. My radian will cancel. The unit will cancel. And we will be left with, the pi is also canceling. What else can cancel? The 2 divides into 180. How many times? What's left? 90 degrees. So we end up with 5 times 90. So degrees, I'm okay that you guys like multiply them out. Don't leave degrees in fractions. Like if they end up being decimals, you guys can write those as decimals. It's these ones that we expect to be written this way as a fraction. Let's hurry and get the specials in our notes so we have them because we use them a ton. And then we're going to kind of go to the next topic, okay? What do you guys think 60 degrees is going to be pi what? Let's try to just analyze before we actually calculate. How many 60-degree rotations can we get in before I get to 180? 3. Because I can go 60 degrees, 120, and I'm at 180. So how many pies, even though we're not really talking about pi, how many pieces of pie? 3. So what do you think one 60-degree rotation was? 1 pi thirds. Okay, so pi over 3. And again, if we did the conversion, 60 times pi over 180, we would have simplified to pi thirds, right? So I'm just doing the more visual representation of this. So one 60-degree rotation is one of my pi thirds because 3 pi thirds gets me all the way to pi, which is 180, right? 1 pi third, 2 pi third, 3 pi thirds, right? Okay, let's do 90. How many 90-degree rotations can we get in? Or we can do the conversion. 90, 90. Yep, those are pi halves. So 1 pi half gets me 1 rotation. 2 pi halves gets me all the way to 180. Right? Okay, how many 45-degree rotations? 4 of them can fit. Because I have 45, 90, 135, all the way to 180. So 4 pi fourths will get me all the way to 90. So just 1 pi fourths is a 45-degree rotation. Now this gets a little backwards because people see a 6 and want to say that's a 60, and people see a third and want to say it's a 30. But isn't something with a bigger number on the bottom actually a smaller fraction? So this is a smaller fraction, so think smallest angle. Okay? How many of us remember these specials from last year a little bit? Did you guys get into radian measures? Some of the honors classes for sure do, and the regulars it's hit and miss. Some kids have never seen it when they come to me, and some have. Okay, I'm moving on to a new topic. Are you guys okay with radian measures and at least converting for now? We'll use the unit circle a little more tomorrow, or Thursday, okay? Now I need you guys to be able to start getting comfortable with graphing the angles, because without this skill, we can't do anything Thursday. Thursday, you will be completely stuck if you don't learn how to do this. Make sure you do your homework on this one. I want you guys to be able to graph in standard position. This should be familiar to you. Do you guys remember naming these quadrants? Quadrant 1, quadrant 2, quadrant 3. I'm using Roman numerals because that's what we usually use, but quadrant 4. Do you remember how we go counterclockwise? That's the rotation you guys go around on the unit circle, and so that's kind of why we go counterclockwise. So a positive angle is going to be counterclockwise. Clockwise, going the other direction, is a negative angle. We always put the initial side, so here's the vertex, we always put the initial side on that positive x direction. Okay? And then you rotate theta is what we always call this rotation angle, and then your terminal side is what they call it. Your terminal side is how you guys draw your angles. So this angle is bigger than 180. Well, we haven't been able to draw angles bigger than 180 in just a little triangle. Your guys' triangles you've been dealing with have pretty much been stuck in quadrant 1. Anything less than 90 is quadrant 1, right? Anything above 90 to 180 is quadrant 2. 180 to 270 is quadrant 3, and 270 to 360. So 360 is a full rotation, is your quadrant 4, and then beyond, okay? We've only stuck with everything less than 90. So you guys have to imagine your triangles have been pretty much stuck to this quadrant. They've all been less than 90, okay? Okay, so when you guys draw your angles, we want you guys to draw it like this, and you do have to have the arrow. People miss it on the test. When I say graph this in standard position, you don't tell me which direction you're going, and so I don't know which direction. So you might have it in the right quadrant, but I don't know what direction you rotated. So I need you guys to have that there. And then we are also going to know that you graphed it properly by their reference angle. So these are reference angles. Reference angles are the acute, meaning less than 90, in each of these individual quadrants. So if your angle falls here, it has to always be formed with the terminal side of whatever theta is and the x-axis. Don't ever drop it to the y-axis. We are going to be graphing triangles eventually, and we're always dropping it to the x-axis. That's going to be dropped to the x-axis. This is going to be dropped to the x-axis, and this is going to be dropped to the x-axis. So when you guys form your triangles eventually, which we'll do Thursday, that's your reference angle. That's your reference angle. That's your reference angle, and that's your reference angle. So when you guys are drawing these reference angles, they always, we use theta prime as your reference angle, and it has to be always 90 or less than 90, okay? So in quadrant 1, you guys can't see this very well. It's a little bit blurry, but hopefully you guys, theta is your reference angle. So 30 degrees and 30 degrees, theta is 30, reference angle is 30. But let's go here. Let's pretend I dropped a little bit beyond, let's call theta 150. So if theta is 150, what would you guys say its reference angle is? We only had how much more to get to 180? 30 more. So for you guys to get reference angle, theta prime, you get to take 180, or theta, or pi I mean, minus it by your guys' angle you rotated to get your guys' reference angles. So in this regard, your guys' theta prime would have been 30 degrees. Your reference angle would have been 30. Okay? We'll get more practice, I promise. Okay? What do you think you do to get this reference angle? Now your angle theta is bigger.
Do you go down to 180?
We actually, close, you go to 180 and then you decide how much further. So since your angle's bigger, you now do theta minus 180 or theta minus prime pi if it's in radians. So these might be in degrees and these might be in radians, okay? So if I have it in radians, then you would do the radian minus your angle, okay? So, and then to 360, I'm not quite to 360, so you do 360 minus your angle to get this leftover. Okay, we'll practice. But it's either 180 minus your angle to get the leftover, or your angle minus 180 to get that small reference angle, or 360 minus your angle to get that small angle. Okay, and it's more intuitive than memorizing this little graph here. So let's talk about it. So I want your guys' skill, before we leave this slide, is to sketch each angle. That's skill number 1. Skill number 2 is being able to label its reference angle properly. Cool? Okay, let's do it. So where does 210 fall? Which quadrant? It is in quadrant 3 because we go 90, 180, and then 270, and then 360 and 0 is this one. And so it falls here somewhere, right? So I know 210 is more, so for me to get my theta prime, I take 210 and I minus my 180 off to get me that leftover. What do you guys get? So let's draw our initial side, and then we're going to go around, and then we're going to draw that terminal side once I know where it's at. So it's in quadrant 3, so 210 is bigger than 180. So I go 210 minus 180 to get this leftover. So how much further beyond 180 did you go to get to 210? 30. Yep, we went a nice little 30-degree rotation to get to that angle. So now draw your terminal side. So you guys will, this was known as theta, and then you guys will label your reference angle, and I'm going to do that in orange. You label your reference angle like this and say, okay, my reference angle, theta prime, is 30. Does that make sense? Theta is what put me there. Theta prime, with a little prime or a little apostrophe, is prime, stands for prime in math, is the reference angle. Cool? Let's do it in radians. Now, how many people think that they would rather convert their radian to degrees? Okay, that's fine with me, but just make sure you report your theta back to a radian. That's expected of you. I feel like that's the longer route, but you are more than welcome to convert, so you can convert. So if we convert, we're going to do negative 5 pi fourths, and we will times by 180 over pi and figure out what that is. So somebody who wants to convert, take a moment to do it. I want to do the other way though, okay? Because I don't want to have to convert and convert twice. You'd have to essentially convert twice. Convert it to a degree, find where it is, convert it back to a radian, you know? So we want you guys to report reference angles in radians if it was given to you in radians. So let's try radians. Here's my initial side, and anybody notice what direction are we rotating in radians? Opposite, the negative way. How many pi fourths is this? Let's break this down. Pi fourths was a what degree? It was a 45 degree. So we are essentially doing 5 times that. So 5 pi fourths, you technically can convert it just a little bit quicker by realizing, now we're not always going to give you specials, but we still need to realize, okay, I can break up pi, like even if it was pi sevenths, right? I know I could get 7 of these before I get to here. Does that make sense to everybody? Even if it's not one of my specials. Okay, let's do special. Let's do 45 degrees for 1 pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths. Did I know that 4 pi fourths would have given me a 180 degree rotation? How many of you already put it in quadrant 2 before I even got there? Yay! If you realize it was in quadrant 2, That's good. You're kind of understanding it. So this is theta. Now I'm not done. You didn't tell me the reference angle, which is right here. So what is theta prime in radians? I went one more what? Pi what? Pi fourths. I went one more 45-degree rotation, whoops, which is a pi fourth. So my reference angle is pi fourths. So that's what's cool, is almost converting the degrees is a little more complicated because this is how many times you're rotating, right? Even if I was doing, let's do something tricky. Let's do 6 pi sevenths, okay? Just something that's not a special. Well, if I rotate 1 pi seventh, 2 pi seventh, and I don't even care, 7 pi sevenths puts me here. So where is 6 pi sevenths going to drop me? Right there, just shy of being 7 pi sevenths. And what's my reference angle? What would theta prime be? One more what? One more pi sevenths to get to it. So you can do it even with non-specials. This is one more pi sevenths just to get to 7 pi sevenths, so I'm just shy. Does that make sense how you can still do it without specials, without converting? Now if you want to convert, we just, what was 45 times 5 again?
225.
You guys hopefully would have realized 225, negative 225 was your degree. So you could have rotated negative 225, did 225 minus this 180 to get this little reference angle. Reference angles are always positive. So make a note, they are always positive, and they're always that special acute angle within that quadrant. So even if you rotate a negative, your acute angles, it's like what angle is right here what positive angle is in that quadrant? Okay? How do we feel about that skill? That slide is its own little skill. Draw in a reference angle, draw it, standard position, and then do it. You'll get more practice, okay? Let's move on to our we got a couple things still to talk about, so I gotta kind of hustle. We want you guys to be able to graph coterminal angles. What do you guys think coterminal means? Use common sense. Use more like reasoning. Coterminal angles. Coterminal, I'm going to start you off. Same. What do you think? Same terminal side. What that means is I need an angle that's coterminal that has the exact same, they land in the same quadrant, same spot, with the same reference angle. So they're essentially the same exact spot as I go around the circle. How do you think I do that? How do you think I find angles that are coterminal and land in the same spot, same quadrant? What do you guys think? You can turn and talk if you want to. What do you guys think I do if I want to find coterminal angles? So I was looking at my notes really fast. Okay. Okay, let's use common sense for a second. If an angle lands right here, let's say that, and here's my terminal side, okay? And I want something that's coterminal, what do I do to get all the way back to that? And it doesn't matter what direction.
You just flip it across the x-axis.
Not really flipping, but you're close. Because if I flip it across the x-axis, it's actually going to put me down here. So I got to end there. I got to have the same ending side. So I've got to have another angle. So my first angle, call it theta, the blue. All right. What rotation is this to land me right back there? 360. Does going the other direction also land me there? Minusing, you're adding 360. Okay, that's how you find coterminal angles. You either add or subtract 360 from it. And you can actually give me infinitely many answers. You don't have no right or wrong answer. You also, if it was in radians, add 2 pi and subtract 2 pi. Okay? Let's do one that's in degrees and one that's in radians. So given an angle that's coterminal, and then make sure you give it the same format. So someone give me something that's coterminal with angle 215. 215 plus what? I can plus 360.
575.
Did you say 575? That one's coterminal. What could I do now? to get another coterminal?
Subtract 360.
I could have done 215 subtract 360. What angle is that going to be? So think about where 215 falls. 215 falls about right here, right? So 215 minus 360. Somebody give me that. Sorry? Negative 135. Oh, 45. I was like, I didn't think that was 135. Okay. Negative 145. Yeah, that makes sense. If I go negative 145, it'll end up in the same spot. I could also have taken 575 and I could have added another 360 to it, which is technically me taking 215 and I could have added 2 times 360. You can technically add 360 or subtract 360 as many times as you want. You could give me infinitely many coterminal angles at the end in that same spot. So does coterminal make more sense now? Okay, let's do it in the same mode, or not mode, same format, same, not degree or radian mode or format, okay? So I want to take pi ninths. You can convert it to a degree, but then you have to convert it back. So let's try to get good at this instead of having to always convert. So I might add 2 pi to it, but then I might also subtract 2 pi. Now here's what sucks is usually radians are in fractions. And so, so you guys usually run into having to convert things to a fraction. These are the next 2 lessons. There you go. We did do a warm-up on Schmoop. It's just added to the bottom of your ACT. I do have to find a common denominator. So what would I do to find a common denominator? Now, is pi ninths a special? It's not a special. It's not a pi fourths, a pi sixths, or a pi thirds. But you still have to be comfortable with these non-specials, okay? All right, so I'm almost there, you guys, and I have a couple of questions like your homework, okay? So hang in there just a little longer. All right, how do I convert this to so I can add these? I need a common denominator, and what would my denominator have to be? Close. Because this has just a 1, let's use something easier. 9. 9's easier. 18 would work. We'd have to convert both of them is the problem. So what do I times by to create a common denominator here? 9 over 9. 9 over 9, right? Like a 1. So if I times by 9 over 9 on both of these scenarios, I get pi ninths plus 18, and maybe that's what you meant, Cam, sorry. 18 pi ninths. Or I have pi ninths minus 18 pi ninths. So isn't 18 pi ninths still 2 pi? But I just got it in terms of having a denominator that's a 9, right? It's still 2 pi. Do we understand how we just converted? Okay. All right, and then I'm able to give me something that's coterminal. I also have seen people do this visually. Like if I'm at pi ninths and I want to add, 9 pi ninths is 180 degree rotation. And that means 2 of those, 18 pi ninths is 2 pi. So some people like do it more visually like that. Like they don't always convert if fractions are scary to you, okay? But I essentially just converted 2 pi to 18 pi ninths, okay? And then we end up getting what? 19 pi ninths, which can't be simplified, or negative 17 pi ninths. So whenever we use degrees that are not specials, we get something that doesn't divide nicely. Pi fourths, pi thirds, pi sixths, they're all specials. But you may have to deal with ones that aren't specials. I want you capable of it and not afraid of it. Okay? How many of you feel like you could find coterminals pretty easily? And this was a last year topic. Does anybody remember this last year? No? That's okay. Okay, last idea. Can you, given a point or given a trig ratio, sorry, there's 3 ways your whole homework is asked. Given points or given a trig ratio, can you guys find it on the unit circle? Can you guys use your information you know, and can you guys find what's being asked, okay? So I have 3 types of homework problems that are going to set you guys up, okay? You're either given a point, theta, or you're given a ratio. And these are how your last 3 sections, let's see, maybe we took off this type. We'll try them. Okay, here we are. I either give you a point or I give you the terminal side of theta, okay? So the terminal side of theta in standard position contains this point. Tell me what theta is. Now, some of these might be specials from last time, so let's see if you guys can pick it out. If you can't, that's okay. What quadrant will -1 root 3 fall within? Hey, is she okay?
She's fine, but she's.
I'm gonna call my hubby really fast. Okay, so, let's finish this one. What quadrant does -1 root 3 fall within? Second, I heard. Good, thanks, George. Is that you? -1 root 3, and I don't care if you're accurate, you guys, these are literal sketches, so that's what's so nice about this. And what's cool is you guys are actually, so imagine an initial side and imagine something rotating, and I'm not going to draw it because I don't want extra drawings, and it ended there. And here's the cool part. You guys are forming triangles that you just got so good at. You get to draw this vertical side, and you guys get to draw this horizontal side, and it's always this 90°, and your hypotenuse is always going to be your radius of your circle. Okay? So what do you call this length of this triangle? -1, that's that length. What's this length of the triangle? Positive root 3. Yeah, you're right. Tell me this then. We want to know what theta was that put us there. Here's the cool part. You guys just learned to find little reference angles. And me finding the setting up a trig ratio within this triangle gives me the answers as long as I have the negatives involved of what theta is. Isn't this kind of cool? So you guys have just done all of this stuff that just set us up perfectly for this. Now, I'm curious, before we get into using trig and whatever, I would rather us not have to set up tangent of whatever, like yet. I wanted to do that Thursday. Can anybody recognize which special this might be? We just learned specials the other day, and we can generate them. So from my 30, what's across from the 30? A 1. What's across from the 60? A root 3. And what's the hypotenuse? 2. Okay? So what is across from this reference angle? And don't worry about the negatives. The negatives are there because it's what quadrant we're in, and they have to be there. But what's across from that?
23.
Yeah? That's our what angle then? What's this reference angle? 60. So tell me, what do you guys think theta is if that's a 60-degree angle? Which one? Yeah. How many of you are able to come up with, or see that? Able to see those kind of specials? Let me hurry and see if we give you anything besides specials on these ones. Okay, let's try this one. Sometimes it's okay if they land on the quadrant too, which we haven't talked about quadrantal angles yet, but we'll talk about those later. Okay, let's try this one. What quadrant does, hurry and set this one up, and can you guys try to figure out what quadrant does -2 fall within?
3.
3. So we're here at -2, so this length is -2. Then my terminal side goes through this point, -2. So that's going to be -2, all right? Take a moment to tell me what triangle you guys think this is, and then in turn, want you to conclude what you guys think theta was. So take a moment without my help. I'm going to pause the video. I'm going to call my hubby. See if you... It's not quite like the 1 root 2 or the 1 root 3 and 2, but we have same legs, which means it's a what? It is. It's an isosceles triangle. This is a 45, 45, 90. So my reference angle is 45. So what did you guys say theta is? 225? Okay. We could have also said the negative direction, and on the test we usually specify if we want the angle positive or negative. You guys could have said the negative direction. So this one is similar to questions 23, maybe 24. You might have to use trig ratios. So let's hurry and do a roundabout approach. You guys can treat this reference angle the same as you getting this angle. So we could have set up tangent of what? What could have we set up tangent when we realized this was a tangent 60? We didn't have to just memorize that these are specials, because they're not always going to be specials. So let's play dumb for a second, pretend it wasn't. What would you guys do on this one? Tangent of 60 is, what's opposite that 60? Root 3 over a negative 1, which is essentially negative root 3, right? And then, hold on, I needed an x. Oh, we didn't know 60. Let's pretend we didn't know 60. Sorry. I was like, I need an unknown. So let's pretend we weren't doing a very good job or it wasn't a special. Does that sound good to everybody? Okay? And so what goes into my calculator when I want to find that angle? Tangent inverse. So I take tangent inverse of negative root 3. Would somebody tell me what that angle is? Tangent inverse of negative root 3. Negative 60. So here's the tricky part. That didn't tell me this quadrant, but what it's telling me is your reference angle is 60, is what it's telling me. So since we're in this quadrant, we would say, okay, my reference angle is 60. I can now guess what theta is. And so since I'm in quadrant 2 with a reference angle 60, I say 120. So you do have to reference what quadrant you're in. These results will always give you reference angles. Sometimes negatives involved when negatives are involved. So don't be thrown off that gave you a negative 60, okay?
Wait, so how do you get 120? Do you just times it by 2? Or what
No, 60 is this, and so I had to rotate 120 to get there with a 60-degree reference angle. Because 180 minus that 60
okay, yeah.
is what gets me there.
Okay, gotcha.
Okay, last one, and then you guys will be fine, I think. The other way your last 6 questions ask you, this is similar to the example I just did, where it's not a special. Is that okay if I skip these ones that gives me an ordered pair? Let's at least do these setup. I want to do this last one. Negative 3, negative 4. So negative 3, negative 4 gives me this triangle. So in order to get theta, we would do, again, tangent of theta is blah, blah, blah. Does that make sense to everybody? So if it's not a special, you can still find it. Does that make sense? So let me do the last way. What if I give you a ratio instead of a ordered pair? So I tell you I want it to be in quadrant 2, and whatever theta is, so quadrant 2 is here, I don't know what theta is, so just kind of play dumb for a second because we don't know what theta is, but you guys always set up your reference angle, always set up your triangle, okay? So go from here. Cosine of it is negative 3 over 5. Where do I put the negative 3 and where do I put the 5? And your radius of your circle will never be the negative 1. Does that sound good to everybody? Your radius is always positive. Where do I put the negative 3 and where do I put the 5? Negative 3 is the adjacent. Good. And then where do I put the 5? Hypotenuse. So now I have asked you guys to give me the 5 remaining trig functions of this function. So, or this angle. I don't know what. I don't know that. So I have to do Pythagorean theorem. Don't let negatives scare you off because they go away when you square them anyway. Oops. So they will turn positive. So we would get 9, 25 minus 9 is 16. So this is a 3, 4, 5 triangle, right? And now we're capable of all the trig ratios. I'm not even asking for theta, you guys. I just wanted the trig ratios, so still leave it theta. So that's all we said was give me the 5 remaining trig ratios. So just to have one under our belt, I would do sine of theta. What is it? From theta, you always go from the reference angle, even though this is theta. So theta prime, go from the reference angle. 4 over 5. That means I know cosecant. What's cosecant of theta? 5 over 4. They gave me cosine, so I know secant. What's secant of theta? Negative 5 over 3. You can just put the negatives out front. And then let's do tangent of theta. Negative 4 over 3, or 4 over negative 3 is right, but I just do negatives out front. Cotangent of theta is negative 3 over 4. and you guys did it. So, I guess what we want you guys to be able to do is to be able to set up these triangles no matter what quadrant they fall in. Do I give you a ratio? Do I give you an ordered pair? And you guys just take your time to set them up. And everything is a triangle within each little quadrant. And just make sure it's always a 90 degree with the x-axis, no matter what quadrant it is. I apologize.